April 5, 2023. Well, if yesterday was about the path integrals and quantum processes, today would probably continue in the same, because it's quite a long topic. To get involved with essentially a kind of simple thing intuitively, that as we infer what we can deduce about its contents from what we stipulate or posit, that what's results posed, we can intuit as a means of triangulation or location gathering or of the sort of a reckoning, that then we can result in the interpolation of that to the connected points of connectives, that what results is a means to establish a causal chain for inference. That inference is in one sense entirely causal, while the intuitive is something to consider along the lines of what's posited or stipulated and what's posed or set up, as what results then. This kind of organization is a casual sort of reflection on the causal with regards to then when we want to establish what is mathematical and proven, that there's what's derived after what's defined, that is the what may be inferred, and usually as in the course of the inductive analysis, the inductive inference, and thus what results from the deductive analysis, that the deductive is at once a wide outer inference, and then as well then it's a specific inference as be the contrapositive, or being able to carry negations unambiguously, so that when something can be eliminated, that the process of elimination results what remains, or deduction. That it's kind of like the absolute and relative, the deductive and inductive inference in the abductive, say. In this, what is conducted, and then in these connectives, what are a sequence in the calculi or calculus of the logical inference, what can be arrived at properties of things for a set theory or a part theory, or categories of things for a category theory or a type theory. And these kinds of modelings of the non-logical objects in what become logical frameworks as of the plainly logical, what overall is the purely logical or totally logically. And so what we had arrived at the other day was, after some of the preliminaries in Swanson's book on path integral and quantum processes, he'd established his working definition for the course of this book, what the quantum process was. And it was in terms of the amplitudes and the bra and ket of about the Gaussian integral, which admits particularly well-defined solutions about the results of these amplitudes summing that are probabilistic and reflect the gradient of what's otherwise something that's totally probabilistic is random. And there's the challenge of basically that anything is at once formless and a vector, or that it's at once a circular and linear, or that it's at once going inward or outward, or as about these conditions, that the contour integral was worked up a bit, that for this notion of the path integral, then what results, again, as was begun here today, a kind of a simple thing, measuring the length of this line, or that a certain distance is traveled in the course of passage of these particles, as what are the elements of particle theory and quantum theory, where quantum theory's elements include particles and waves. That, as we've been talking about in the nonlinear theory and the potential theory, about a theory of some potentials, that the sum of histories model, or sum over histories, as the author puts it, is a usual formalism. So that then from what we intuited, there are results that we intuit that there's a strong need for formalism, for things to be well defined. And then from the setup, we intuit what would be properties that can be defined so simply as reflect models that are already well known in their connectives, and how they can be represented as reasonable things that we lead back to how to make these sensible, fungible, and tractable, those being desiderata of any given reasonable thing. That then there's the question of, well, what does it mean to pose and posit these things, where posit is the stipulation and pose is the setup, or what's picked among all the stipulations and all the connectives and all the relations, what to project outwards to look to see what might be connectives under there, and then to build what would be connectives among those chains of inference, where we establish the causal in the chains of inference. And in that manner, we can reflect that causality is, which is considered inviolable in physics, and which is considered necessary in logic, that it results then for what we intuit it, that we don't need to carry around the whole formal development in each spelled out letter detailed part, is that it's so composable. We've encapsulated it in the sense of software engineering as a thing with a boundary instead of a thing with such detail, and the ornate, that's the symbolic or representational as instead of the value or the ornate. That then it's the results that then we'll be able to talk about what result then from those lower level concepts that are ultimately first order, on the order of the first order, that these higher level concepts result, that then we can treat that as first order. And so then when we talk about type theories and inverting the diamond, which is the notion that there's a hierarchy, and in its depths then it's brought back together some other reasoning apparatus about mapping a path over it, that this notion of the path integral then becomes much the same thing in this space of realizations. This is particularly about the realm in a continuous manifold called space-time, about the propagation of particles, and under the considerations of what these particles have as their properties, because they're defined as probabilistic. The path integral and its path elements is according to the superposition of states that a particle in quantum mechanics has, due to the fact that it's really modeling a probabilistic distribution, which is really modeling a superwave formation or some superclassical real explanation that mathematics is totally yet grasping toward. That the sense of making it so, this same notion of the path integral or wayfinding in inference then results then what it takes to explain in detail and a course through this path is in much an analogy the same kind of thing. And this is among reasons why they say that a lot of people who study physics go into fields like finance or the actuarial, because a lot of the same kinds of approaches that go into minimizing and maximizing or finding straight lines and these kinds of things end up applying in other systems that have this sort of emergent behavior, and as to where what can be modeled as the probabilistic is not very tractable in the overall sense, and especially when there's the interaction of distributions with regards to something like Bayes and Jeffries, where usual probability theory is built with Bayes priors, that's conditional probability, and that there's also the notion of Jeffries priors. And so what does it mean when there's these prior causal conditions that result these post probabilistic conditions? It's among these reasons why it's important that overall knowledge of the calculus is available to explain these lower level concepts in sufficient detail to connect them to the lower level connecteds of the methods, so that above that there can be the higher level methods of the analysis for applications. So there's discussed the Hamiltonian Jacobian equations and the reading into chapter 2, where he establishes his definition. The standard version of non-relativistic quantum dynamics will be reformulated in terms of a path integral. As a limiting expression, we talked about the fact that the path elements were as of a iota-values or a metrizing ultrafilter, which is basically a thing in topology built high above standard analysis. It's the same thing as the low level iota-values. Infinitesimals, they range from 0 to 1, and infinity of them, it's a certain non-standard standard. That he continues, the relevant aspects of basic quantum mechanics are reviewed in this first section, and then the sum over histories is introduced, and we talked about this Hilbert space and its inner product, and about the gimbal lock, and there's the introduction of Planck's constant and h bar, which is normalized in a sense, and we talked about normalization and denormalization, and how the renormalized was at once denormalized, and the reasons why that helps explain and is helped to be explained by the fact that it's a probabilistic interpretation of what is a deterministic thing in a superwave. That there's talking about phi and psi, or phi and psi, imagine time ordering, and the time ordering convention was written so that, and then the notion of this raw differential d dt, the partial derivative with respect to time of phi t equals delta t, Dirac's, I imagine, that that's a particular result as after what it could be shown to be a couple different things, but it's shown there as in accordance with the way the integral representation is built up, that it ends up being the terms that approximate what was presented as the functions that go to Dirac's delta in the limit. Dirac's delta is intuitively a flat line with a spike at 0, and the spike goes to infinity. And although this spike has 0 width, the area underneath that spike equals 1. So it's a non-standard function, and it's a very important kind of thing, kind of like the radial basis function, which is a bump at the origin that has area 1, or the Heaviside step function, or the equivalency function, natural unit equivalency function, or sweep as I call it. These are non-standard functions with real analytical character. That the integral of the equivalency function is interesting because it's a discrete function, but it has an integral, and its area is 1/2. Or 1, variously in accordance whether its convention is set up. So, in the Heisenberg picture of quantum mechanics, the observables are time dependent. So then when we talk about this partial respective time of d dt phi t equals delta t, the differences in time are vanishing, so it's very carefully contrived why that is so, and it's because it's a continuous quantity, and without otherwise it's maintained that it was a continuous quantity, then it would so fall apart. It is necessarily so ultimately attenuated to be a flat line with a finite value that goes into the derivation, that goes into the derivation of that particular quantity within the overall frames of these connectives, that in this little box in the little diagram, and as so how it's connected, that it has that qualifier on it. The equality of the matrix elements in the respective pictures, these Heisenberg pictures, are the Heisenberg of brass bracket psi, big O, Heisenberg of T, phi, Heisenberg equals S, Schrodinger, psi, comma, T, pipe O sub S, pipe phi, comma, T, Schrodinger. So according to these tensorial representations, according to these definitions and derivations. It's so set up for the Heisenberg and Schrodinger, their tensorial products, these integral representations of the Heisenberg picture and the Schrodinger picture, that these elements of the tensorial and built into the bracket notation as a center bit, or where they hold in terms of the Hermitian and the adjoint and the various things that enable the setup of the Hamiltonian and the Jacobi after the Jacobi. That big OH of t is written as e to the I big H t over 8 Planck bar h bar times O of h e to the negative I h t over h bar. So it's a differential equation set up in terms of the coefficient in front of the integrand is as times the function itself and the constant. So there's a particular kind of property of the exponential function that is own derivative. And so here it's as that it's this own, it's the particular property of the function that is own product of this transformation. And so that's where operator calculus comes in, or operator algebras, is to be able to work on these functions as they are like the operator calculus of differentiation of differentiable functions that happen to be their own antiderivative, or this kind of function that happens to be defined as equal to itself as about this scaling constant in terms of what's applied for the Gaussian, this e to the I h over h times t over h bar, and Heisenberg, that this is, and I'm not quite familiar yet with this development, but it's so setting up that, and that way we would talk about it usually in terms of the operator calculus for something like, oh, it just so happens that this little diagram of Feynman blows up to this in this representation where the only connectives can be written as according to this Gaussian integral, that it so results that they mean the same thing, although when you look at either one particularly, it has to contain all the other connectives of its connectives, in a sense, of its causal, and it's well defined in its behavior. If H is explicitly time dependent, then it is necessary to use time ordering. He's so relating that otherwise this would not be well behaved, or it would have unreasonable values, or would not maintain its system of units, or it would, and they wouldn't have an interpretation in the model. The Heisenberg picture states that the kets psi h are time independent. It is clear that the Schrodinger picture and Heisenberg picture can be chosen to coincide at some specific state. So it is clear. Sometimes when it's said it is clear that, then that also means there's an unclear other meaning. Or it is clear that is like it has to, because otherwise this thing doesn't fall apart. So it's really highly contrived to put it this way. So this is one of the things that when you read in the mathematical writing, it is clear or it is obvious, that usually when it's obvious, it means it's obvious and there's only one way. But when it's clear, then sometimes there's something else about it that's unclear. And it just kind of depends on the tone, and otherwise that this is for the intuitive to admit that it is not like it is so that. It is uniquely so that. It is uniquely so that if and only if that. Those being more causally defined, that this reflects point of style from the author reflecting that it's not. And it includes some of these comments I make about it. In what follows, it will be assumed that this time is t equals 0, and any state with no explicit time dependence displayed can be considered to be either a Heisenberg picture state or a Schrodinger picture state at t equals 0. If the path integral formulation of quantum mechanics, the object of utmost interest in it is the transition amplitude. Well, the amplitude is the measurable, the observable, and there's how it implies the carriage of the energy and the force that gets carried by the force carrier in terms of these time-dependent systems. If the system is in the Schrodinger picture state, ket psi comma t a at the time t a, then the transition amplitude to the state psi tb at the time tb is defined by z psi phi equals bracket psi comma tb given phi. The pipes read earlier were given in the conditional probability as according to Bayes, who has an alternative in Jeffries at least. And it gets into, and after about parastatistics in terms of the derivations of probability theory and classical probabilities and non-classical probabilities. Comma T A. The transition amplitude then gives a probability, and the transition amplitude Z, it then gives the probability of the system transiting between the respective states as P equals absolute value of Z squared, so that Z describes a quantum process. So again, this is a representation of the quantum processes followed up and after reading more deeply into the definition of the pictures, that this was reached in an earlier reading as that this is the output, and it's as of after the inner product taken that of this amplitude that results in square. So we've been dealing in roots, as it were, and then it adds up for all the usual things to do with roots and squares in probability theory, like the variance and the standard deviation and the Central Limit Theorem. That what's assumed in this probabilistic interpretation, and it's not really addressed here in this book, has to do with the Bayes theory and the after Bayes, B-A-Y-E-S, and the Central Limit Theorem, which is that the distributions with a mean, which is an average value, which has the highest probability in the CDF, PDF, or MGF respectively of being the value of a sample. Not necessarily that it's likely, but it just has the highest probability, the mean. And that things with a tendency or propensity to the mean, like these things that kind of fill in the middle of what's the path element and kind of stripe the line that then gets rolled in this measuring wheel, that P equals absolute value Z squared, so that Z describes a quantum process. In the next section, the transition amplitude is given a path integral representation. 2.2, the path integral derived. Now, when we say derived, I mean, this is kind of a definition. So a part of it is derived, but what we'll be looking for is what sticks out is what's defined, what is posited, what is stipulated. In this section, the transition amplitude will be given a path integral representation by applying the results of the previous section. The pivotal idea, first noted by Dirac, is that the infinitesimal quantum mechanical transition amplitude is governed by the value of the classical action. So the action and the action potentials and the sum of those is a usual thing. And it represents the impulse, it represents the change of phase, it represents a lot of things, the action. And that violence is a word that originally means lots of action. Using fairly intuitive arguments, this idea was developed by Feynman. Here it's mentioned fairly intuitive, and whether they're fairly intuitive or fairly intuitive is again a matter of style and reading and a bit of wonder, where the idea of the natural language is to make it so that it expresses thinking about the thing besides just reading it off. This idea was developed by Feynman into the path integral representation of the finite transition amplitude. Finite here meaning well defined as a value, as a real value, and also as a non-infinitesimal value, and that as they're summed together the quantities, that it emits a value that's a finite value. So what finite usually means is as the result of bounded computations that results yet another bounded computation. What it means here is as a result of summing over infinite many terms that results a bounded value. And later presented in detail in the book by Feynman and Hibbs. The path integral derived in this section will be identical in form to that first developed by Feynman. However, derivation based on the canonical structure of quantum mechanics has the advantage of demonstrating that the path integral must yield results identical to those obtained by the standard methods of wave mechanics or matrix manipulation. Here, I'll be interested mostly in the wave mechanics as of about the wave and resonance theory and the nonlinear contributions, theory of potential, theory of harmonic functions, and what results some theory of some potential or theory of higher order, highest order resonance, filling out the box. The path integral derived in this section will be identical in form to that first developed by Feynman. However, a derivation based on the canonical structure of quantum mechanics has the advantage of demonstrating the path integral must yield results identical to those obtained by the standard methods of wave mechanics or matrix manipulation. ... For that reason, it is an immensely valuable heuristic device for testing generalizations of the path integral form to systems where a rigorous derivation is impossible. So he might be describing various systems where the coordinates are out, or where the conventions are out, or where things are contrived, or there's other inputs, or there's bad data, or anything else that goes into reasons why it results that what results is essentially a guideline of sorts for an path integral that has a certain particular tractable definition and derivation under these other conditions that are so usual, like the Gaussian, which don't always hold or may not be so, or the Bayesian, which don't always hold or may not be so, or these other reasons why, then what results is a good little fire truck that blocks when you want and rolls when you want and sprays water. It is therefore very important to list the assumptions that go into this derivation so that they may be kept in mind during any generalization. So here, as I was just mentioning, he's mentioning this. First, it will be assumed that the limits on the statement of completeness are plus minus infinity. That's not so unusual in real values. Second, it will be assumed that the Hamiltonian H has no explicit time dependence, though this is not necessary. As we were talking about in the nonlinear setups before, when in Malgain's book, there's conditions where the Hamiltonian, or the setup after the tensorial transformations of propagation of action and collection of it in time, and how it's integrated, that similar quantities as the abstract quantities in the configuration space, the position and the as of the inputs, the energy of the thing. That's just an example where the Hamiltonian has explicit time dependence when, for example, it reflects that it is as of those nonlinear inputs resulting more nonlinear contributions than linear contributions, destroying the otherwise usual notion that the classical input is dominating, because it so results that it is not. And that is not that the error term is dominating and becomes simply intractable and that there's no forward progress, but instead that there is basically the right-hand turn or the orthogonal or the curvature or what results that, this is not necessary. Sometimes when you see this is not necessary, it's important to disambiguate that from this is necessarily not so. Sometimes I'll hear somebody say something that's like, oh, well, that's not necessary. And what they really mean is, like, if that were so, then I would be toast. And so it's, again, just sometimes necessary to carefully go beyond what's the negatory and disambiguate it as what's necessarily not versus not necessarily. Third, and this is for simplicity of notation, this system will be considered to be that of a one-dimensional single particle moving in a potential. A potential. This is where the idea is that the field lives in a potential. So this is kind of like a univariate, in a sense, problem and challenge for this approach, because there's, as we've been talking about in the nonlinear fields, when we have other fields that are opposing, and those are set up neatly when they're directly opposing. That's one reason why Malgain's work in the nonlinear electromechanical effects and applications is it has to do with basically putting it all together. And so this is in terms of a potential field that basically a particle follows this electrical particle or has charge will follow the potential according to charge. And maybe in accordance to whether it interacts in magnetizable regions or is magnetizable, where it does with the magnetic field that crosses it. But here, it's only saying that there's one potential field, and so there's only one gradient. So when all we were talking about the gradient or the overall direction of flow or the current or the flux, the fleeting of the flux, that we in our classical flow models and our superclassical flux models, that in this system it's that of a one-dimensional single particle moving in a potential. The first step in the derivation of the path integral is to construct the instantaneous eigenstates ket q comma t and ket comma given p comma t of the Heisenberg picture operators qt and pt. These are defined by ket qt equals e to the iht over 8 Planck given q, and ket pt equals e to iht over h bar given p, respectively. It is to be noted, so these Hamiltonians are set up as these Heisenberg pictures in these eigenvalue problems to then set up their instantaneous eigenstates as with regards to the partial derivative of time convention that was described. It only follows as after the quantity is built up as after the path elements is according to the iota-values. It is to be noted that these states are not Schrödinger picture states. However, these states are complete, he follows, that being where the Schrödinger states have those different conditionals inside about the wave versus the particle. However, these states are complete since it follows from ... that the integral from negative infinity to infinity dq of given q comma t, the q comma t times bra q comma t, reversing ket and bra, equals the exponential of iht over h bar. That's to be read off as a single thing. Exponent of iht over h bar is a quantity after a convention, and then it's also about the transformation rules of the tensorial products, and it's also with respect to its complex quantities through the Gaussian, and all the Gaussian that has to do with the exponential, and then also with respect to the representation in the amplitudes of those as kind of range from 0 to 1 as they're mapped from -1 to 1. And that sounds a bit contrived, perhaps at the end, where it's very clear that what this really has to do is after the Gaussian integral and eiht over h bar, that bringing h bar in is an arbitrarily small constant that's still finite and often is taken to go to 0. That then when this is present in these equations as a quantity, that's e to the iht over h bar is to be read as one quantity, and a notation, just like Leibniz's summation bar is read, integral s for summation dx is read as summation, as a convention and a quantity, and to avoid the use of the word quantification because it means something, and to avoid the use of the word quantization of something because it means something, and quantification, quantization, a convention, convention in the quantifying CQ of the quantity negative infinity its integral of ket dq given q, i.e. irrespective of time or not time dependent, times the exponent of negative iht over h bar equals 1. So that results what's an identity that these the product of these two functions results 1, these two quantities, that then is treated, you can treat that as normalizing, meaning whatever you have that you have replaced the parameter with 1, then it cancels out of all h bars. You can add and remove it to either side, or deal with 1 on one side and this on the other side and cancel it out in a sense. And usual settings where the standardization and normalization is applied in probability theory, that here it's so contrived that this is how the states are complete. And then he reads that the state ket q comma t is an eigenstate of the Heisenberg picture operator qt, in the sense that qt times ket q comma t equals q ket q comma t So that it's not that Q, big QT equals Q, but that their quantity results in this, that it's so canceled out that they do, so that the original Heisenberg picture operator is replaced by the value, or vice versa. These states also, and that's contrived and only taken with care, because it's readily wrong in a lot of readily derivable senses. These states also have the valuable property that for psi comma t, a Schrodinger picture state, q comma negative t of ket psi comma t equals bracket q c psi equals psi of q. So here he's helped show that it reduces all this extensive algebra and these quantities after the Gaussian, after the dot dot dot. Results that the reason Gaussian makes it all complex and stood up and spun around and bracketed out and pulled back in and then dropped down and left out is the result that it cancels out. A similar pair of statements holds for the instantaneous momentum eigenstates. These states can be used to derive the path integral form for the transition element between Schrodinger picture states. The object of interest z, the amplitude of the previous section, is defined as the inner product of the instantaneous eigenstates at different times, so that z qa ta qb tb equals bracket qb comma tb c qa comma ta. So that the A is the initial condition and B is the subsequent condition, where it is assumed that TB is greater than TA. It is. Knowledge of the form for Z allows the calculations of the more general form, since it follows that the transition element between Schrodinger picture states is given by bracket of psi negative TB phi negative TA equals this integral from negative infinity to infinity of dqa, dqb, so an integral in both those amplitude functions the product of the kets substituted and the brackets substituted in as per the valuable property a Schrodinger picture state has such identity that reduces to then after the adjoint being placed back in, or that psi star qb psi qa replaces the Schrodinger picture state, or is according to that property an identity, an equality rather, where if we might say, well, an identity is when you can resolve that something equals 1 or 0. But it also means that it's an inequation. That here it's an inequality after a substitution of terms according to algebra when the conditions of variables do not interact, so it's possible to have them aside, that then it's also contriving that the sum is over dqa and dqb, as that's the width of the stripe of the path integral that's being drawn in a sort, so that they kind of have to be about the same or not arbitrarily larger or smaller than each other. This is kind of an assumption that goes into this 2.31. It follows that the transition element between Schrodinger picture states is given by this formula in psi of qa and phi of psi of qb and phi of qa and z of the initial amplitude of qa ta qb tb, and that's where it results at. So that z is in the overall amplitude transition. So that the equals bar is like the value to be found is still under the integrand, so that becomes a problem in differentiation where it's defined, or this is how it's derived, that he set it up that the quantity of interest, these eigenstates, are now within this integral equation. That's how it adds up. And so now we need to break it down. Once the initial and final states of the system are specified by the normalized forms for psi q and phi q, the system propagates in time from psi to phi. I suppose that's theta. No, that's phi. up and down is phi, side to side is theta, through the function z. For this reason, the transition element 2.30 is sometimes referred to as a propagator, since it contains all the information regarding the time development of the system. So when we say propagator here, it really reminds me again to recall the interpolation. And an interpolation is basically drawing a smooth curve between 2 points that reflects that there's a straight line or another curve connected to 1 point. And it's to be interpolated from that point to another point. And the idea is to draw the smoothest curve that's the most natural between those 2 points. And so this might be accomplished, for example, as by connecting a pendulum, finding a pendulum and just drawing an arc of a circle, or some tautochrone, or some catenary, or some parabola, or some hyperbola, or the French curves, or what are the Bezier, or what are the points of interpolation, or methods of various multi-point interpolations, or that otherwise then this propagation is as a broken this down into elements that for this straight line of a sort, because QA and QB are about the same, and B minus A is not very large, and there's it's not a very wide stripe, this line we're measuring, that it's interesting to figure out then what interpolation is, as it's all kinds of these things, and that there's kind of this classical and non-classical interpolation, and it's about this potential theory is what enables to draw potential theory is that all these fields of potential stake themselves out in the interpolation. And so that then what becomes the minimizing and maximizing function between those, which is that it's minimized, that it's different from the potential at each point, and so is carried along, otherwise in constant uniform motion and line drawing, like iota values in sweep. That's fundamentally the act of drawing a line at constant uniform rate of time. That it so results that thus this is pretty much the derivation so far of the path integral, and now we need to figure out how to find out what are those elements. This gives that z of QA-TA, QB-TB, it reads here, the time he describes and defines propagator. The time interval TB minus TA is first partitioned into n infinitesimal steps of duration epsilon, or I might call it iota. Epsilon equals TB minus TA over big N, where the limit N goes to infinity is understood in everything that follows. This is what was read yesterday, now with a bit more of the preamble filled in, that it's finding out what are these derived and defined assumptions. We're rereading this section in a bit. That next N minus 1 complete sets of intermediate instantaneous Q eigenstates are inserted into the transition element sequentially at each of the respective times. Tn equals TA plus n epsilon. These were the Dirichlet principle, box principle, Dirichlet's box, pigeonhole principle, the ordering, the time ordering, and these things put together. And this gives z, QA-TA, QB-TB equals this integral of the partials in the n's, a bracket QA comma TB, bracket QN minus 1, TN minus 1, times QN minus 1, the bracket of QN minus 1, TN minus 1, given ket QI minus comma Q1 comma T1, and Q1 comma T1 bracket QATA. That this involves that there's basically reading from the left and reading from the right, and so for the infinitely many in the limit, from the left and from the right, it's added up the distance that combine the one way, kind of accumulating per the equivalency function and stacking on up, and then dropping down the other way, kind of as the reverse equivalency function, which starts as 1 and drops in a constant tone monotone decreasing standard difference infinitesimals to 0. The sum of which their integral is 1 or 2, according to the convention. This is so written this way that that's it under the limit, as it's so written. It's intuitively that it's even really is as so, and could be written in a much more brief notation, given that as a convention of a limiting function. Each one of the infinitesimal transition elements may now be analyzed. Since the time difference is epsilon between the two states, it follows from the definition that the jth element is given by bracket qj plus I tj plus I of qj tj equals qj plus 1, and that c is the e to the negative I epsilon h pq over h bar. qj. So, and here epsilon is arbitrarily small infinitesimal in this quantity, and h bar is arbitrarily small infinitesimal quantity in the systems and measuring the units of measured quantities of particle physics, and represents that floor beneath which is the Planckian regime, and the trans-Planckian regime, real mathematics of infinitesimals and infinities, whatever it is, that then these only exist mostly as of a quantity over themselves, yet they still also represent this instantaneous differences that they're interpolated among the elements from beginning to end, how it so arrives it from this to that. Carrying along over the course of the path these transitions in the probability amplitudes. In order to proceed further, it is necessary to select a convention that will be used consistently to reduce all the infinitesimal elements. To evaluate the matrix element of the exponentiated Hamiltonian, the exponential must be expanded in a power series. And when here he says must, it's like this is what we have. Maclaurin and Taylor, power series, a series in terms of usually increasing order, that as their values are between 0 and 1, or they're so normalized that the terms diminish. It's a series of powers in order, that because the terms are between 0 and 1, the terms diminish, thus that it may approach a limit, and the initial terms have most of the contribution. That this is the convention because that's also the available tool. After the expansion, all the P operators would move to the left and all the Q operators would be moved to the right. For want of a better name, this is referred to as coordinate ordering. All right, so this is as we were reading yesterday, and then this is coordinate ordering again. The final result of coordinate ordering, a product of P's and Q's, will be that all the P operators lie on the left side of the expression, and all the Q operators will lie on the right side of the expression. So that is, again, kind of helping to close this box, and to result that then when you look at it from a higher level, that you can kind of see that directionality on the box of the connectives that are available at various scales, various pyramidal scales of resolution of these connectives of our Swanson's quantum theory's path integral and our theory of intuit and infer connectives path integral and plan. That all the P operators lie on the left side and all the Q operators lie on the right side, as via a reflection principle, simply. The coordinate ordering operation will be denoted by C coordinates, so that, for example, C of P Q P squared equals P Q Q. Obviously, the opposite convention can be selected. The opposite, again, is that the ordering is reversed. And it is natural to consider the possibility that the existence of different ordering schemes might introduce some ambiguity in the resulting path integral. It's similarly as with the coordinate schemes. When you have different ordering schemes, you might have different coordinate schemes. We have different things that establish the metric, the norm, the distance, and the angle, and the measure of the angle. And these are, at least in our planar coordinates, quite a variety of things there can be. There's even a third form of coordinates, I forget, that's kind of apropos in the planar. And that these then get into like Kriskales on the outside of the black hole, and Schwarzkopf on the inside of the black hole, and Chandrasekhar on the inside of the black hole, and Kerr on the outside, and this kind of thing. The advantage of coordinate ordering is that an arbitrary function of Q and P, denoted by FQ comma P, has the matrix element bracket P is C F Q P Q equals F Q comma P bracket P given Q. So that a coordinate ordered function of the operators may be reduced to an C number, classical number function, by taking its matrix element. So we've had this eigenvalue problem set up. And then it results that what comes out of it is coordinate ordered functions that it gives a number, or finite number, kind of, as it talks about. We talk about classical number Result can be demonstrated by using a power series representation of the classical number function f and by noting that the coordinate ordering suppresses the presence of any commutators between q and p. That the notion of this coordinate ordering is that by reading out the terms and assuming a gradient and an impulse to the path, that it's basically giving it a spine of a sort, and then that it's sort of regular how much or little it can flex in a way. And so that results that then the outer, it's assuming that only an inner product of a sort exists, that there wouldn't be contributions that could vary on the amplitude of the outer product that come back and cause, anything else. Thus that in a probabilistic sense it will usually add up and maybe give a good probabilistic numbers, which still eventually would suffer the notion that, well, after all, they're only probabilities, vis-a-vis the causal and the deterministic, that it's a conceit. And that so thus the commutators are suppressed, or what would result reflection principle causing feedback of a sort according to that an object and its inverse obey commutativity or anti-commutativity, any commutators, where that would basically reflect a binary affirmative or negative property about whether or not otherwise that could be ignored in a simpler system, for example. Whereas, so the next step in evaluating is observe that e to the negative I epsilon h p comma q over h bar equals c negative I epsilon h p over q over h bar plus big O of epsilon squared. The proof of this statement for a general Hamiltonian is given in exercise 2.2. However, demonstration of particularly simple but physically meaningless form h equals ap plus bq is instructed because of its use of the Baker-Campbell-Hausdorff theorem. The operator version of this theorem is identical to the form provided in section 1.4. We looked at a little bit. Using this theorem shows that e to the negative I epsilon ap plus bq over h bar equals e to the negative I epsilon ap over h bar, e to the negative I epsilon bq over h bar, e to the I epsilon squared ab over 2h bar. So that the effects of the commutator are big O of epsilon squared and are therefore irrelevant in the epsilon goes to zero limit. This is where, as above, it kind of follows from the earlier conventions and the original conventions that establish the linearity of this thing, and you can imagine another field placed on top that would skew it around, as it were. Since the commutator represents quantum effects, here effects meaning usually changes in a boundary, but here it just reflects also anything that falls outside the model. It's like, here's where he says, here's where there might be dragons, Since the commutator represents quantum effects or quantum corrections, this verifies the intuitive notion that for infinitesimal time periods, the time development of the system is overwhelmingly dominated by classical dynamics. This is where the usual computation of the path integral, where it's like, my classical computation of this this particle's path is 1.0000000. I've computed the path integral and it's 1.0000018. 0.00000. That usually these path integral effects, when they show up, are out at about the 6th or 7th order of magnitude. Sometimes when they talk about, it's like, oh, you need 6 sigmas to show something. It's because otherwise you haven't gone past where the path integral will show up. Sometimes. This verifies the intuitive notion that for infinitesimal time periods, the time development of the system is overwhelmingly dominated by classical dynamics. The generalization of this result, showing that the big O of epsilon squared term in 2.36 is ignorable, can be accomplished by using the Trotter product formula. If A and B are any two bounded operators, the Trotter product formula gives exponent of t, quantity a plus b equals limit as n goes to infinity of exponent t over n a, exponent t over n b, all to the n. And that's just like the natural logarithm there, and then you take the logarithm of the exponent and get a neat value that equals in the product and drop out. And so you need something about the something else. If you want to, you would need some identities in factorial and exponential to solve some of these kinds of things. Prove 2.38 and adapt the theorems to demonstrate that in the epsilon goes to zero limit, the commutators generated by a Hamiltonian of the form h over p squared over 2m plus vq are irrelevant to the evaluation of 2.33. The commutators by a Hamiltonian of the form h over p squared over 2m plus vq are irrelevant. So p squared is the first one's Heisenberg, and 2m is the mass of the particle, I must imagine. And that vq is the velocity in the q Hamiltonian, if I'm not mistaken. Then the reason why is because those two are after the coordinate ordering, resulting that it's as fundamentally as per p on the order of p, it's p squared times vq or p of q. That it just results that the same results follows for the rest of the thing. I can't say that I don't have an answer for that, but I'd be looking at it in that means. It's been posed, this question, after what's been posited. This setup has been posed, and so then I'm using my intuition to arrive at, via interpolation, to what connectives I have available, how to plug that in the limited search space that the brain has, and about right now. But it's here later if it's to be picked up and built out into a system of theories. Sometimes you solve a problem just to crunch out an answer. Other times the whole point of solving a problem is to solve the kind of problem. These results show that the infinitesimal transition element 2.33 becomes, for example, epsilon on the order of 0, an expression in the bracket of q to the j plus I. These elements of q plus j are the next and previous element, as about the inner term being this Gaussian integral bounded Heisenberg picture, where h bar down. This infinitesimal element can be simplified further by we end up getting an expression in terms of the bracket of qj plus 1 pj and pj qj of these two related amplitudes. Is about the related time ordinals and the related elements in the quantity in 1 over 2 pi h bar, where we brought 1 over h bar out, we brought 1 over 2 pi out, and what's its result is probably after the differentiation thus, and of the term again in the e to the ipj q j plus I minus qj, in the finite difference or infinitesimal difference there is what results. It's arithmetic difference. Ypj and the arithmetic difference of the qj are related over h bar, which is brought out by some differentiation. Thus said, I reached a point where I'll stop, and section 2.2, and so we've got about 40 formulas into 2.2 or so. Let's see where we started here. We started on a formula. We started in this section on formula 2.30, 2.26, and got up to about 2.40. Oh, and the next section is sum over histories. So sum over histories is, we'll get into kind of the talk about the potential theory and what. Well, that's about it for today, I suppose. Let's take a look here. What does Feynman have? If we take one of these Feynman lectures, volume 2, and we play a phone book, which is open it up and start reading. Reflection and refraction of light. So we got refringens, birefringence, reflection, refraction. Reflection and refraction refer to the geometric properties of a ray of light. This is that reaching a reflective surface that has any number of considered flat areas, and however it may be curved, but usually a flat mirror, that the geometric properties of light make it as that the reflection angle is the incidence angle. And thus it results that a ray orthogonal to the reflecting surface is reflected directly back, and a ray incident to a surface is reflected off that surface in the same direction as the ray in the plane of the ray after its reflection in this with the same angle incident. And then refraction is, and what he says is the angle of reflection is equal to the angle of incidence. All right? Maybe I read ahead that and just, regurgitated it. For normal incidence, any polarization. So what we want to emphasize that the amplitude of a surface reflection is not a property of the material, as is the index of refraction. The index of refraction then is, as of course in a translucent material, where an opaque material admits no light through it. A transparent material admits all light through it. And everything really is in between, and it's called translucent. And so the translucent material has an index of refraction, which reflects why when you look at things underwater, it's per the angle of refraction. And so he just says that outside it's geometric and inside it's optical. So the light's waves travel basically per the geometric, straight lines, reflection, and that breaks down into diffusion and stuff like that, and the specular, and when we have different kinds of reflections from different kinds of materials and different kind of media that they reflect over. Why is the sky blue? And this kind of thing, and then why otherwise do images form? We learn in a physics class about the formation of the image and the focus of the image and these things to do with light, and we look at great admiration to somebody like Fresnel when it comes to these things. Fresnel is who I feel kind of had some of the most intuitive grasp of light as it behaves. And then refraction is as of in water or some of the medium, it is bent. It's going through a prism where different wavelengths of light are refracted variously. That if there's a really good book about the rainbow, Carl Boyer's The History of the Rainbow, and in it he describes the effort over time to determine A, the colors in the rainbow, and B, the angle of the rainbow, and C, the conditions in the real world under which the rainbow exists. And it's a mathematical history of the theory of the rainbow. And Descartes gets a lot of credit. That's basically one of Descartes' bigger contributions in mathematics, is his work in his field of analysis. He went all busy on the study of this problem of the rainbow and cranked out a bunch of things and came up with some good ideas about how at the time he had the best numbers for the computing the curvature of the rainbow and its radius given its ends and this kind of stuff. And then there's Fresnel, and then Airy, and so Airy is up there, A-I-R-Y, Airy, up among those people who really brought it forward to the next level, the theory of the rainbow. And then there's Young, and Young's also familiar from work in physics. And so Airy, Fresnel, Descartes, and then there were earlier people and some later people, but Boyer's book on the rainbow is a great book. So anyways, in this lecture, Feynman is talking about I'm talking about the geometric, which is like a billiards game, it reflects perfectly, and the optical is that it travels as a wave and about and around, and that the focus is what it follows. The refraction through a media carries an image as of the optical. The value as about the curves and edges of things is about the optical. So geometric, straight lines, optical, wavy. All right. And then he gets into classical fields and the electromagnetic field, and Feynman really likes to having everything end up being an electron, because then he deals with everything in his electromagnetic fields and the mathematics thereof in terms of, for example, figure 34.6, the two possible energy states of an electron in a magnetic field B, vis-a-vis the infinitely many superpositions, or what results from the classical Bohm, beyond the classical Bohm de Broglie real wave function, these things. So yeah, you can find that some of Feynman's greatest facility is in the mechanics of the electron, in electron theory. Well, all right. There's much more for this to give it due credit, but at least he gets into kinetics, the equations of motion, Bernoulli's theorem of flow when we get into fluid mechanics, and fundamental theorems in flow mechanics, as we talked about before. Anyways, I hope you enjoyed this reading today. What it was a rereading of the section 2.2 to get some of the deeper detail of what's going on in terms of the context and the things that a skimming, a quick reading was able to extract a linear development and basically acknowledge that it goes on and be able to fill in some of the context as what fulfilled the linear part of the development, which makes it possible to read at all. Then this other part, the intuiting, is expanded quite a bit more in detail in terms of what are the assumptions that go into it and what are the possibilities and the limitations that come out of it. So in this manner, as I also started describing how some of it can be rewritten much more concisely in some of these frameworks of a non-standard function like the equivalency function, with its caveats of limitations and qualifications, just like the Dirac delta is a non-standard function that with its limits and qualifications fits and is neat and is linear and complete for what it is. That's the kind of thing that I would carry on in usual course, trying to condense a work, to expand the work, then to write a program, then to be able to put numbers in and get numbers out, make path integral calculators. Well, all right then, until another day.